And astroquery.mast is basically an entirely Python module hosted by AstroQuery that allows users to make download and query requests directly to several of our MAST APIs. But for this demo specifically, I'll be showing you how it accesses the portal API. And working with AstroQuery MAST is pretty similar. It parallels with working with the portal on the website. But with AstroQuery MAST, you are working under the hood and communicating directly with our databases. So you do have more control over the type of queries that you make. You can query with the same criteria, but you can also query with specific JWST databases that will allow you to do science instrument keyword searches. And if you are a user who's planning on making bulk downloads, then this would probably be a good way for you to go about it. So for this notebook specifically, I'm going to be introducing you to just the basics of AstroQuery MAST. I'm going to be showing you how to make observation queries using our main database's criteria, using the 3 query techniques that are available to you. I'm then going to show you how to get the relevant products for these observations, and then I'm going to show you how you can download those products directly to your local computer. And then the last part of this notebook is going to be showing you the batching technique that we recommend in MAST that will allow you to download your products as efficiently as possible, but without overloading our system. So let's go ahead and jump into how to query for observations. So there's 3 ways that you can query for observations. You can query using a set of coordinates, both in hour, angle, and decimal degree units, and that's with the method called query region. You can also query with the target name. So if you don't know the coordinates of your target, that's totally fine. You can work with a method called query_object. I won't be showing you that one just for the sake of time, but just know that it's available to you. And then the last way that you can query for your observations is with the observational metadata, which I've mentioned to you before, and that is with a method called query_criteria. So I'm going to go ahead and demonstrate to you what a query region call looks like. So I'm going to be querying for NGC 3132. So a call like that looks like this. So I'm just assigning an obs_table variable to an AstroPy table object, which will be created when I call the observations class. And the inputs for a query region are the object coordinates, and then the second required parameter is the radius. But keep in mind that the radius is a keyword argument, so you do need to be explicit that you're feeding it the radius. So you set radius equals 1 arc minute, and then I'm going to go ahead and show you all the results that we return. But first, let me do a quick import. And just as a quick preview, the imports that we're using are AstroPy, AstroQuery, which wraps around AstroPy, and then lastly, I'm importing matplotlib for plotting purposes at the end of the notebook. And it looks like it's taking a while. I think I might have to reset. Okay, good. Okay, so running the query, and we get 251 observations from this single query. So let's go ahead and display the contents of this table. So what I'm doing right now is filtering out for a column called S region. You don't need to do this. I'm just doing this for the sake of the notebook. This column is basically going to give you like a set of vertices that make up a polygon that covers the footprint where your target lands. It's a useful column to have, but it does clutter the view, so I'm just getting rid of it by masking that out. And then let me just show you the first 5 rows of the table. So this is a standard AstroPy table object that would get returned for an observation query like the one I just did. You can see that there's 5 observations here with a bunch of columns that are the metadata that are used to describe each observation. So you have things like filters, wavelength region, the target name, the RAN declination in decimal degrees, and things like that. So that is query region. I'm going to skip query object because I'm constricted with time, but you go ahead and feel free to test that out yourself. The query is pretty much the same, except you're calling query object, and instead of feeding it a set of coordinates, you're feeding it the name of your object. If it is resolvable and part of one of our catalogs that are used in AstroPy, then it'll work. Otherwise, it will not. So the last method I'm going to show you is query_criteria, which, as I mentioned before, is going to be using the metadata that you see in this table to filter out and get your specific observations. So let's go ahead and introduce you to the get metadata method. So off the bat, you probably won't know all of the metadata that's available to you. There's about 33 different metadata that you can work with, that you can query with. So if you don't remember what you can work with, there is a call here that you can use to get all the metadata. And it is under observations, so I'm calling observations.get metadata. The metadata that I want is for observations, because I am querying for specific observations, and then I'm just going to do a show in notebook call so it doesn't truncate my table. And this is the list or the table of metadata that you have to work with. So there's a total of 34, I think. This is 0 indexed, yeah, 34. And the values under column label probably look familiar to you. Probably you will be working with the values under column name, not column label. And the reason why is because with AstroQuery MAST, you're basically working under the hood directly with the main database. So you need to speak the same language as the database speaks. So for example, if I wanted to query for a bunch of JWST observations, the mission is JWST, but I will be using the obs_collection metadata for this query. So let's go ahead and use an example of this. So I'm going to do a metadata search that combines the observational metadata and also the coordinates. So it's going to be kind of like combining query criteria and query region into one. That's the cool thing about query criteria, is you can also do a regional query on top of all the other metadata that's available to you. So let's go ahead and assign obs table to the AstroPy table object that we're going to query. And the method I'm using is query_criteria. Let's get only the JWST mission data. So I go up and I see that the metadata counterpart of mission is obs_collection, so that's what I used. I only want to look at Mary images, so the instrument that I want to work on is Mary. So the metadata equivalent is instrument_name. So that's what I'm going to put in here. Instrument name is equal to Mary. The program ID I want to work with is 2733. So let me go into the metadata table and look for program ID or proposal ID, which is interchangeable to MAST. So the metadata equivalent is proposal_ID. So let's put that in as well, 2733. And last but not least, let's throw in the coordinates and the radius the same way that I did with query region. So coordinates is equal to object coordinates, and radius is equal to 1 arc minute. And you actually don't need to feed in a sky coordinates object for query region or query criteria. You can feed it just like a string in RANDEC without the comma. But just for this case, we're just working with the sky coordinates object. So let's go ahead and run this. And let's go ahead and show you the contents of the table. Let me just show you the first 10 rows. Oh, there's only 4. Okay, so let me filter because we have S region, the S region column, so it's kind of cluttering things up. Let me just show you data product type. You can also filter by columns this way, just similarly to like indexing a list. Show you OBS ID and data URL. And let's just show you instrument name to show that we are indeed only working with MIRI. Okay, so that is the AstroPy table object that's a result of this query. And now we need to get the products for these observations. So step 2 is retrieving the data products, and a call to the data products looks something like this. So I'm calling observations again. I'm calling a new method called getProductList. And I'm not going to get all the products for all 4 observations. Let me just get the products for just the first row right here for this first observation. And I'm going to show you exactly how many products get returned from a query like this. Because it is, you can potentially get like even thousands of products for a single observation. So in this case, I'm getting over 3,000. And the reason why is because there are a bunch of auxiliary products that come alongside just the raw science images. And you're also getting stage 1, stage 2, stage 3 level products. So it adds up and you end up getting, you could potentially get thousands of products for a single observation. But let's take a look at just the first 10 rows of the products, and this is what a standard product output looks like. Let me just single out a couple of these columns that I think are relevant to you. So let's do size, let's do calibration level, let's do product file name, and I think I'm good with that. Okay, so here we have product subgroup. Okay, actually I want product group description. Yeah, so here we have all of the individual products that are part of that first observation from the table above. You can see that we have calibration level 3 and 1 in this index alone. And you'll also see that we have a column called subproduct group description, which flags some rows as minimum recommended products and some as not. So let's go ahead and get only the minimum recommended products for this products call. And as Dick mentioned in his presentation, the minimum recommended products, or MRP, are basically the minimum amount of products that you need to download that will allow you to do your science, but will not overload your computer. So you won't be downloading a bunch of unnecessary files like guide star acquisition files and uncalibrated files. So let's introduce you to another method called download products. And we are going to feed it the products that we got from the previous call, but we're only going to download the minimum recommended products in total. So there is a caching feature in astroquery.mast, which is clever, and it'll look to see if you have already downloaded the file that you're trying to download now, and if it exists already, then it will not replicate the download. So that's what you're seeing here. And then the other thing that I wanted to mention is this info message right here that says only downloading 605 unique products. Obviously, we're only downloading 5 products, so that doesn't reflect what's really happening. This is a result of a recent addition to AstroQuery MAST that calls duplicate products. So JWST makes duplicate products because you could have the same guide star acquisition product or the same ASN product for multiple observations. So this is basically just getting rid of the duplicates, and part of the new feature was outputting an info message that lets you know when the culling happens, but it doesn't reflect when someone puts MRP only equals true. So this is actually what you would be downloading if the MRP only flag was false. So if anything, it's a testament to how filtered down your products get after MRP only is set to true. But yeah, this is doing what it's supposed to be doing. It's just the info message is a little misleading. So that's something that we need to work on in the next quarter. But we have the downloaded files, so let's take a look at what this output is. So when you download products, it'll output an AstroPy table object, which I've assigned to this variable called manifest, just for the purpose of the notebook. And manifest is basically just kind of like a log file that gives you an update on all the files that have been downloaded and their relative paths. It gives you a status update of the downloads and some other information. So let's use this manifest output to extract only the science file, which is the file on this third row right here, so that we can then do some plotting. So I'm going to do some quick enumeration. So for index, file, in enumerate, manifest, I'm indexing for that first row, the first column. If I2D is in the file name, then I want to assign index to that index. And the file is going to be assigned to file, local path. I have the index now, and then let's just make sure that file gets indexed properly. So yeah, this is my file. And the relative path, it automatically downloads to your current working directory. So now let's read the data. So I'm doing a quick fits.getData. I'm calling the file, not specifying an extension. It's just going to get the first science extension data. Okay, so now let's do some plotting. So PLT figure, I'm going to set my canvas to 8x8. And then I'm going to do an imp show of the side data, normalized and reoriented the proper way. And now we have NGC 3132. So that is just a simple example of how to query for observations, get the relevant products for those observations that you need for your science, download them, and play with them on Matplotlib.